Hi, I'm going to talk about Ensemble of Deep Convolutional Neural Network with Monte Carlo Dropout sampling for automated image segmentation quality control and robust deep learning using small datasets. Deep learning has been popular for medical image segmentation research, but even state-of-the-art deep learning method with overall good performance can still fail on unfamiliar testing data. This example shows that deep learning-based automated image segmentation method falsely recognizes the breast implant as part of the myocardium. If this kind of error is not detected, it can affect clinical parameter estimation and possibly also clinical decision-making, potentially undermining the interests of patients. Therefore, case-by-case inspection of segmentation quality is necessary, but manual quality assessment is laborious, time-consuming, and prone to inter- and intra-observer variability, especially for large-scale imaging data. Having an automated pipeline for image segmentation quality control is desirable. A popular framework for automated segmentation quality control is by generating multiple segmentation candidates that measure the similarity or differences among the candidates to predict segmentation quality in the absence of manual ground truth. How do we generate multiple segmentation candidates? A popular approach is by Monte Carlo sampling. A convolutional neural network can be implemented with Monte Carlo dropout units activated for both training and testing to generate many different segmentation candidates for quality control purpose. But one disadvantage is that the candidates are less diverse compared to other approaches. Another popular approach to generate multiple candidates is deep ensembles. Multiple convolutional neural networks are trained independently to generate different segmentation candidates, but this approach is more expensive to train compared to the Monte Carlo approach. For example, if you want to generate 100 segmentation candidates, then you need to train 100 neural networks, and that can be quite expensive. But it has the advantage of having better candidate diversity, which is important for robust quality control. In this work, we aim to combine the advantages of both. There are 3 stages for this framework we proposed. The first stage is to generate segmentation candidates. For the same input, we apply an ensemble of multiple units with Monte Carlo dropout. Each unit generates 20 Monte Carlo samples. Then we use the median segmentation from each unit as segmentation candidates. We can also generate combined segmentation as candidates by pixel-wise label voting scheme. Essentially, the median segmentation are added together pixel by pixel to generate a label voting map. Then we apply different thresholds to generate the combined segmentations. The second stage of this framework is quality prediction. We measure the inter-candidate DSC in a pairwise manner among all the segmentation candidates, including both the median segmentation and the combined segmentations. Then all the inter-candidate DSC values are supplied to a regressor implementer for each segmentation model to predict the ground truth DSC, which is the DSC measured between the candidate segmentation and the ground truth manual segmentation. The last stage of this framework is to select the most optimal final segmentation by choosing the candidate with the highest predicted DSC. This on-the-fly selection mechanism can improve segmentation robustness. We applied this framework on the Sunnybrook cardiac MRI dataset of 45 subjects, consisting of normal controls, heart failure with ischemia, heart failure without ischemia, and hypertrophic cardiomyopathy. They were manually contoured for both endocardium and epicardium and diastole, and that's what we used for training and testing in this work. We didn't use the data at end systole because only the endocardial contours were available. 7 subjects were chosen for testing consisting of 1 normal control and 2 cases for each pathology. 38 subjects were chosen for training with data augmentation. And this is the result for the segmentation performance. The table shows that the proposed framework outperformed all the candidate segmentation models. And in this example, you can see the proposed framework generated more robust segmentation compared to the best unit and the best combined segmentation. For quality prediction, the scatter plots show the proposed framework predicted the DSE very accurately for all the candidate segmentation for both the endocardium and the epicardium. We apply a threshold of 0.7 for binary classification for good and poor quality segmentation, and obtain a classification accuracy of 98% and 99% respectively for the endocardium and the epicardium. We also implemented a Monte Carlo-based quality control method proposed in the literature for comparison. It was implemented by averaging the pairwise DSE values among the Monte Carlo samples. And we can see that there are some obvious overestimation for the DSE prediction using the Monte Carlo-based quality control method. This example showed that overestimation can be a serious issue. The ground truth DSE of this automated segmentation is 0.14, and that means the automated segmentation is poor quality. But the Monte Carlo-based quality control predicted the DSE to be a 1.9 and falsely classified it as good quality. And this kind of overestimation by the Monte Carlo-based quality control is undesirable. We further investigated this example for sample diversity. On the left-hand side, we have the candidate segmentation generated by the multiple units and combined models for the proposed framework. And we can see that there is high diversity among candidate segmentations, and that's why it was predicted with low DSE for this case by the proposed framework. On the right-hand side, we have 20 Monte Carlo samples generated by a single unit. The candidate segmentation look very similar to each other, and that's why the Monte Carlo's quality control falsely overestimated the DSE. From this example, we learned that the proposed framework can generate high sample diversity, and it is important for robust quality control. To sum up this presentation, we propose a novel deep ensemble framework integrated with Monte Carlo-based sampling and optimal segmentation selection. It achieved excellent segmentation performance with accurate quality prediction. The proposed framework outperformed conventional single Monte Carlo dropout-based convolutional neural networks because of highly diverse segmentation candidates. The framework is robust for learning on small datasets, and in the future we'd like to perform large-scale testing to further evaluate its performance. This is the end of my presentation. Thank you.